welcome to another video on rotation. So we were talking about, in the previous video, we were talking about a rotating body and the speed which with something is rotating. So see an example. We choose an indicator line to indicate the orientation of the body. So here's a disc which is I'm looking down on that from an angle, and here is an axis. So this is axis of rotation, passes through in the middle, and we had imagined an indicator line. So you can imagine I painted a line, so when it's rotated, the line kind of rotates and tells me how much is rotating. So it's an indicator for the orientation of the disk in space. Sometimes you would, in the future, we will try to do it like this. We can say this is along the x-axis, and there's a y-axis going that way on the disk, and so this axis will be along the z-axis. So you might think that way if you like, right from the get-go. So this rotating is going around and working with an example. So it went around once and then went around twice, and then this line ended up at this angle. It ended up was 30 degrees. So this was t equal to 0 direction, and this was a t equals to 3-second direction. So this thing happened in 3 seconds. So delta theta was 2 full rotations, 2 times 2 pi, plus 30 degrees, which is pi over 6 radian, and time it took to do that, 3 seconds. So this is like a distance went, and this is time. So I can divide delta theta by delta t, and this should give me the rate at which it's rotating, average rate. It might have been speeding up, slowing down in the middle, but this is a total angle it has covered. So we say average angular speed, and that will be, I take a delta theta over delta t, and so if you look at it, I have a 3 seconds here, and so it is 25 over 6 pi radian. So you can see the unit is going to be radian per second, and it's going to be I'll just leave it as a ratio here. I'm not going to complete the whole calculation. So this will be radian per second, or rad per second. And this is you should note that this is we're looking at average angular speed. This is when we look at a instantaneous speed, like we want to know what's happening at a particular instant. Well, what do we have to do? Can you guess? What we have to do, what happened as t equals to 1 second. So if I look at what happened at or near a particular instant, say t equals to 1 second in my example, in this example. Well, you'll say, you know what, you do more or less the same thing as you did over here, but you look at very near to what's going on there. So maybe, you know what, t equals to 1 second, it was, marker was at t equals to 1 second. Then you say, well, I want to get very close to that. Maybe this is t equals to 1.01 second. 10 millisecond later is over here, and maybe this angle is maybe 10 degrees. Okay, so you'll say that, you know, around here I will have average speed delta theta delta t near t equals to 1 second. You might decorate all of this just to tell what you're doing. So that's actually between these two times it took 0.01 second and it went 10 degrees. Well, I want to write down the same unit. That's 10 degrees will be 180 degrees is pi radian. 10 degrees of pi over 18, so pi over 18 radian, and it is 0.01 second, so this will be 100 pi over 18 radian per second. Very different than that, but that one is an on average what happened, and this is, if this happened over here, this is telling me what's happening around here. If I got even closer to it, so if I imagine doing this experiment one more time, so this is t equals to 1 second, but I looked at really t equals to 1.001 second, and so this angle is even smaller than 10 degrees. Maybe it's a half a degrees. Okay, then if it's a half a degree, then delta theta over delta t near 1 second is a better, this is better indicator than this of what's happening in 1 second, because I got even closer to that. So it's half a degree, but this is 0.001 second. That's the difference in time. And if it's 1 degree is pi over 180, half a degree is pi over 2 times 180 radian over 1 over 1000 here. So this is gonna flip, and it's gonna be 1000 over 1 times pi over 2 times 180, and so this is 50 over 18 pi radian per second. For a while I was thinking I got the numbers off. That's why I'm quiet over there just looking at what is going on. So you can see that this process of continuing, you know, so you do it close and close and close, and that is called instantaneous speed. As you notice that, you know, I get this number and I get this number. Where do I stop? You know, where do you stop? And that's where you need what is called calculus. Calculus has a process by which it will it walks you through and say exactly when this stops and becomes doesn't jump around like this. It may become very steady. Like if you get smaller and smaller time interval, it doesn't change very much. You know, so that's called instantaneous speed. And that's the speed at this moment, we say. We need some kind of symbol for all of these. Average speed, we use letter omega. Average, so this is omega. And for it's the instantaneous, we just use omega. We don't decorate with instantaneous. It's just omega is instantaneous. you might say, okay, I got average velocity, average speed and instantaneous speed. What's the instantaneous angular velocity? We remember we did the velocity before for regular velocity. So if I have something rotating, again, disk is a very simple example to study. So it has nice axle about which I can rotate as an axis, and so if I'm over t that instant, and this is rotating at that instant, and angular speed omega is, let's see, it was 50 over pi, maybe it's actually 33 over 18 pi. Suppose it was that, so that was the answer. Suppose I just picked up a number like that, okay? So I don't know exact number, so it's just the number I picked up. So at this instant, it's like that. So what is the, this is the angular speed. How do I say angular velocity? Well, angular velocity has to have a direction. So is it rotating this way or rotating this way? Which way is rotating? Well, it was rotating this way. So if I look at from the axis, I am going to see a counterclockwise. So I have omega equals 33 pi over 18 radian per second. This will be counterclockwise. So this full information about the rate at which rotating and which way is rotating, this will we call angular velocity or instantaneous angular velocity. And I remember the whole thing is we're going to use the same symbol omega for it. We're not going to put an arrow and things like that. Although you could put an arrow here and say, you know what, I want to distinguish angular velocity vector with angular speed. And this is kind of a strange way to say the direction. You could say, well, it's along this axis. So the axis direction is the direction for this angular velocity. Another way to write this will be, because this is counterclockwise, we can just say angular velocity omega is plus 33 pi over 18 radian per second. So when we say this, what we are saying is, we are basically saying is component, because plus and minus. So what we mean that if I had an x-axis here and the y-axis that way, so x-axis and y-axis and z-axis will be this way, then what we mean is omega in this way, the z component of this is plus 33 pi over 18 radian per second. That's what we mean. You can say this is very consistent notation, because if I was rotating other way, if it was going, this was the axis, and instead of rotating this way, it was rotating that way, So this is the x-axis, and this is the y-axis, and this is the z-axis. X and y are both in this in the plane of the disk. So this is the t equals to 1 second mark. So I'm looking at omega at that. So if I did that, this omega will still be 33 pi over 18 radian per second. Suppose everything was the same in terms of magnitude, but this will be clockwise. So this will be instantaneous velocity, or we can write as omega equals to minus 33 pi over 18 radian per second. Or we can say omega sub z is equal to minus 33 pi over 18 radian per second. So sometimes when you write like this, it means you are thinking a vector notation for the angular velocity. So this is these are all angular velocity. This is angular velocity. While how fast it's going, how fast is 33 pi over 18 radian per second. That's angular speed. Okay, so I'm going to stop here. In the next video, we're going to say if something is not going steadily, but maybe speeding up or slowing down. For instance, when you put something in the centrifuge, it's initially at rest, but when you start to spin it, it slowly picks up speed. So we're going to talk about the situation in which it's picking up speed. When you turn the centrifuge off, it slows down and to a rest. So it's slowly losing the speed, slowing down. So that is a concept of angular acceleration, right? Angular acceleration or angular deceleration or deceleration. We're going to talk about that next. I'm going to stop here.